Ever wonder why a balloon shrinks in the cold or why a bike pump gets hot? It all comes down to an invisible dance. Welcome back to Master the Chaos. Today we're cracking the code of the ideal gas law without a single math equation. To understand gas, you have to stop seeing it as a stuff and start seeing it as a collection of trillions of tiny, restless dancers. First, let's talk pressure. In the world of atoms, pressure isn't a force from outside. It's the cumulative impact of these tiny collisions. The more often they hit the walls and the harder they hit them, the higher the pressure rises. It's total chaos, but with a pattern. Then there's volume. This is simply the dance floor, the amount of space these particles have to move around in. And finally, temperature. In thermodynamics, temperature is just a measurement of how fast those dancers are moving. High temp, they're sprinting. Low temp, they're barely swaying. When you combine these three, pressure, volume, and temperature, you get the ideal gas law. Let's see how they trade places. Watch what happens when we shrink the dance floor, decreasing the volume. The particles don't have anywhere to go. Because there's less space, they hit the walls more often. Result? The pressure shoots up. This is why a compressed air can feel so powerful. Now, what if we keep the volume steady but turn up the heat? This is where things get energetic. As the temperature rises, the particles move faster. They hit the walls harder and more frequently, driving the pressure through the roof. This is exactly why you should never throw an aerosol can into a fire. The internal pressure will eventually win. But what if the container isn't rigid, like a balloon? If we heat the air inside, the particles want to hit harder. But instead of the pressure rising, the balloon expands. The volume increases to give the fast-moving particles more room to breathe. This relationship is the heartbeat of the modern world. It's what pushes the pistons in your car and spins the turbines that light your home. Now, why do we call it ideal? Because in the real world, atoms have their own size and they sometimes stick together. In our ideal model, we pretend particles have zero volume and never attract each other. It's a simplification, but a brilliant one. At the scales we live in, the ideal gas law is so accurate it might as well be magic. It lets us predict the invisible. So remember, pressure is the collision, volume is the space, and temperature is the speed. They are all locked in a constant, predictable trade. When you see a balloon shrivel in liquid nitrogen, you're seeing the law in action. Slow particles mean less pressure, which means less volume. As it warms up, the energy returns, the dance speeds up, and the dance floor expands once again. Chaos mastered. Thanks for joining me, James, here at Physics 101. Join us for Lesson 5, where we explore the hidden energy of phase changes. Don't forget to subscribe and check out the full playlist to master the chaos of the cosmos. See you in the next one.